So our overview and review of the chemistry associated with the different classes of enzymes, focusing a lot on cofactors, has taken us one extra day. And I kind of figured that would be the case, which is why I put in an extra day for like the big chimera activities. So we'll just sacrifice that because at the end of the day, this stuff is getting a firm hold on this, a firm grasp on this is going to help you understand a lot of the chemistry the rest of the semester. Okay, so today we're just going to kind of wrap up, and we'll have plenty of time to do some recaps on some of the important stuff we saw on Tuesday. Okay, so lyases are enzymes that catalyze the cleavage of bonds without using water, right? And we talked about this and we saw some lyases on Tuesday. So we're going to quickly review the chemistry that those lyases, like how they do their chemistry, especially focusing in on the cofactors, right? Like how we use the electron sinks. We talked about three important electron sinks, right? And remember, an electron sink is something, it's basically just a positive charge that draws electron density. And ultimately, the value of that is it weakens a bond enough because we have a place to push electrons all the way to where they can stably be housed temporarily as an intermediate. Okay, and one of those electron sinks we saw in the mechanism for this enzyme aldolase. This is one of the key enzymes in glycolysis. It's where we go from a 6-carbon chain to 2 equivalents of 3-carbon chains. And remember, when we tried to do this mechanism without using an electron sink, what we ended up with was an oxyanion on this oxygen, a negative charge on this oxygen, and a double bond between carbons 2 and 3, right? Because the way this happens is that we have a general base that deprotonates that oxygen. The electrons flow through, this bond is broken, flows up to make that double bond, and then these electrons move up to that negative charge. Okay, so that is not the worst intermediate in the world. It's called an enolate, right? Because it's an alkene, and then we have the oxyanion, so an enolate. It's not the worst intermediate in the world, but it is a high energy intermediate because oxygens don't necessarily want to have that negative charge. Okay, enzymes have ways of stabilizing them, but it's still a reasonably high energy intermediate, which we always want to avoid if we can, because high energy intermediates correspond to high activation energies, which correspond to low reaction rates, right? So the idea here is that this enzyme has evolved an alternate strategy which replaces this oxygen with a nitrogen from a lysine side chain in the enzyme. Okay, and this we have seen already is called a Schiff base, right? When you have a nitrogen double bonded to a carbon and that nitrogen has a positive charge, that's called a Schiff base, okay, or an imine. So now the value of this is if we push electrons now, what we're going to see is that we end up with a nice stable place to put these electrons. Our base deprotonates the oxygen. The electrons flow over to make a carbonyl between, they're on carbon 4. That's how we break the bond and end up with 2 products instead of 1. The electrons move up to make our alkene. And now instead of going to that oxygen, they end up going up to this nitrogen to give us a nice intermediate where the nitrogen is neutral. And then we can kind of reverse this electron flow, and that third carbon can pick up this last proton. Okay, so this was the first example that we saw of how we can use a Schiff base as an electron sink. Okay, and there are lots of other examples where Schiff bases can serve as electron sinks. Okay, they always form in place of a carbonyl, right? So if you see a carbonyl and in a proposed mechanism, you end up making a negative charge on on that oxygen, perhaps the enzyme has evolved a Schiff base. And usually, well, always, I would tell you that that is how things have evolved, right? But being able to understand how and why the presence of this Schiff base makes this a more energetically feasible mechanism is important, right? Again, I want to stress that there absolutely are enzymes that do use an intermediate that's an enolate or even an enediolate, meaning two negative charged oxygens on two subsequent carbons. There are enzymes that use them, but they're not as fast, they're not as good, and they have to use pretty remarkable strategies to stabilize that truly high energy intermediate. The presence of the Schiff base completely bypasses that need, and the enzyme can be a lot faster. Okay? Any questions about how Schiff bases work? Okay. We also saw Schiff bases when we saw how amino acids get anchored onto our PLP cofactor, right? Okay. Some other important cofactors we talked about that also serve as electron sinks. We talked about pyridoxal phosphate, right? So in pyridoxal phosphate, this carbonyl is replaced by a nitrogen, which forms a Schiff base that makes a covalent linkage to an amino acid, and that's how these PLP cofactors always work. Okay, and we saw that the value of that is that ultimately one bond on the alpha carbon is linked down to this nitrogen, and this nitrogen would be protonated. So it's going to have a positive charge on it. This nitrogen is the electron sink when we're dealing with PLP as a cofactor. Okay, and we'll see how this works here in just a second. But the idea is pretty simple, is that, right, so this oxygen gets replaced by the nitrogen of our amino acid. I can't write there. With the nitrogen of our amino acid. I think that I froze my PowerPoint. Yep, it's frozen. Cool. Maybe it'll come back sometime. Did it come back? No. Shit. Okay, so this oxygen is replaced by the nitrogen of our amino acid. That nitrogen, of course, is attached to the alpha carbon, and one of the bonds on that alpha carbon, either the CH, the carbon CO2 minus, right, the carboxylic acid, or the side chain, are in the plane of the pi system that's linked all the way down to this nitrogen. So one of those bonds is labile, one of those bonds is reactive. And every single one of these PLP mechanisms boil down to electrons getting pushed down to this nitrogen and then being pushed back up. They're almost always, I can't think of a single example where they're not subsequent steps. In one step, you push electrons down to this nitrogen so that you can break a bond. In the very next step, you push electrons back up and make a new bond. Okay? So whenever you're dealing with this cofactor, just remember that. Push electrons down to the nitrogen and then reverse it to make a new bond. That's how they all going to work. And